Okay, let's unpack this. Today, we're doing a deep dive into something that's, well, pretty fundamental to so much of the technology shaping our world right now, artificial neural networks.
Yeah, absolutely. Think of this as your shortcut, sort of, to getting really well informed about what these networks actually are, where the ideas came from, and why they've become so incredibly important.
Right. We've dug into a bunch of material. Specifically, we're looking at excerpts from the Wikipedia article on neural network, machine learning, and we've tried to pull out the most important nuggets of knowledge and insight for you.
hmm Our mission here is really to guide you through this, help you see what's most important, and maybe connect some dots between the history, the mechanics, and the real-world impact.
Hopefully, you'll have some aha moments along the way, maybe even some surprising facts.
Let's hope so.
So let's start right at the beginning. What are artificial neural networks really at their core?
Well, at their heart, they're computational models. The inspiration definitely comes from the biological neural networks in our brains. That incredibly complex web of neurons.
But it's not a direct copy, right? More like inspired by it.
Exactly, far from a direct copy.
Hmm.
But that biological idea, that structure, it sparked the whole concept.
Okay, so we have these simplified sort of artificial neurons, sometimes called nodes.
Yep, nodes. And these nodes are linked together by connections, kind of like the synapses in the brain, metaphorically speaking.
And crucially, these connections, they have a numerical weight associated with them.
Precisely. That weight is key. Think of it as determining how much influence the signal coming across that connection actually has on the receiving neuron.
Okay.
So a neuron gets signals from all its incoming connections. It multiplies each signal by its connection weight, sums them all up, adds a little something called a bias.
Like a baseline nudge.
Sort of, yeah. And then this total weighted sum goes through what's called a nonlinear activation function.
And that nonlinear part is really important, isn't it? It's not just simple addition.
Hugely important. It introduces complexity. It decides if the neuron fires, essentially, and how strongly it sends its own output signal along to the next set of connections.
And these neurons, they're organized into layers.
Correct. You typically have an input layer, which just takes in the raw data. Then you have one or more hidden layers in the middle. That's where a lot of the computation happens.
The heavy lifting.
And finally, an output layer that gives you the final result, the prediction or classification or whatever the network's trying to do.
And when people say deep learning,
That just means the network has at least two hidden layers, sometimes many, many more. Stacking those layers is what lets them learn really complex patterns and representations from the data.
right, and that ability to learn from experience, that's the magic, isn't it? Pulling conclusions from complex, maybe even seemingly unrelated information.
That's the power, yeah.
Yeah.
Which is why you see them used for everything from predictive modeling and recognizing patterns to solving really tough AI problems.
Okay, so that's the basic structure, but how do they actually learn? How does the training happen?
Right, training. That's the process where the network adapts itself to perform a specific task. You basically show it lots and lots of examples.
And it adjusts itself based on those examples.
Exactly. The goal is to tweak those connection weights we talked about and the biases too, to minimize the errors it makes
Yeah.
and, improve its accuracy over time.
The source mentions something called empirical risk minimization. Sounds fancy.
It does, but the core idea is simpler. It just means you're trying to find the best set of parameters, those weights and biases, that minimize the difference between the network's predictions and the actual correct answers, at least on the training data you're showing it.
Okay. And how does it actually do that adjustment? You mentioned backpropagation.
Yeah, backpropagation is the workhorse algorithm for training most neural networks these days. It's a gradient-based method.
Gradient. Like slope.
Kind of, yeah. Think of it like this. The network makes a prediction. You compare it to the correct answer and calculate how wrong it was. That's the loss or error.
Yeah.
Backpropagation is then this really clever, efficient way to figure out how much each individual weight and bias in the entire network contributed to that overall error.
Ah, so it traces the error back through the layers?
Precisely. It sends that error signal backwards through the network layer by layer, and by doing that, it calculates the gradient, basically the direction and magnitude of adjustment needed for each weight to reduce that error.
So it's like assigning blame for the error to each connection.
That's a good way to put it, yeah. It divides up the error responsibility.
Mm-hmm.
Then you nudge the weights slightly in the direction that should reduce the error next time.
And you just keep doing that over and over.
Exactly. Make a prediction, calculate error, backpropagate the error to get gradients, update the weights, repeat with more data, thousands or millions of times. It's iterative.
And the hope is that it doesn't just get good at the training examples.
Right, the ultimate goal is generalization. You want the network to perform well on totally new, unseen data that it wasn't trained on. That's the real test.
The source had that simplified example, detecting starfish versus sea urchins.
Yeah, it illustrates the idea you train it on images, and it starts associating features, maybe ringed texture and star shape means starfish, striped texture, and oval shape means sea urchin.
But it's not perfect.
No. So if it sees a sea urchin that happens to have a ringed texture, it might form a weak, slightly conflicting association, like, ringed usually means starfish, but this was a sea urchin.
Okay.
Then later, if it sees a real starfish, it might correctly identify it. But that faint memory of the ringed sea urchin, plus maybe some other confusing features, could potentially trigger a weak, false positive signal for a sea urchin too.
So it shows how these associations are built up across many weights, not just one-to-one feature mapping. It's complex.
Very complex. Real networks use incredibly intricate patterns of weights. And that Python code snippet mentioned in the source, well, it's just an abstract representation of that core training loop. Initializing the weights, feeding data forward, calculating the error, using backprop for gradients, and updating the weights. Rinse and repeat.
Okay, this is where it gets really fascinating for me. We think of neural nets as, super modern AI stuff, but you're saying the ideas,
Right.
they go way back.
Oh, incredibly far back. Some of the core mathematical ideas are surprisingly old.
Like how old?
Well, the basic concept of a linear network and fitting a model to data to minimize error, that goes back over 200 years. People like Legendre and Gauss in the late 1700s and early 1800s.
Seriously, what were they doing?
They were using the method of least squares, which is essentially linear regression, to predict the movements of planets based on observations. That's fundamentally about finding a mathematical pattern in data to make predictions.
Wow. So fitting patterns to data isn't new at all. It just didn't have the computational power back then.
Exactly. And the specific idea of connectionism, this brain-inspired model where memory and processing are sort of intertwined, unlike traditional computers with separate memory and CPU.
Von Neumann architecture, right.
Right. Connectionism started taking more formal shape in the 1940s with researchers like McCulloch and Pitts. They proposed these early non-learning computational models of neurons.
And then Hebbian learning came along. The neurons that fire together, wire together idea.
Yes. Donald Hebb's work in the late 40s on neuroplasticity was huge. It suggested a biological mechanism for how networks could actually learn by strengthening connections that are active together. This concept influenced many early learning networks.
Like the perceptron.
The perceptron, definitely, and later things like the hot field network. And even before the perceptron, people like Farley and Clark were simulating Hebbian networks on early computers in the mid-50s.
But the perceptron was the big public splash.
It really was. Frank Rosenblatt's perceptron, built in 1958, was one of the first implemented ANNs. It got a lot of press, U.S. Navy funding. It generated immense excitement. People thought, thinking machines were just around the corner. Some call it the golden age of AI.
But then things cooled off. The AI winter.
Yeah, that hit hard, especially in the U.S. around 1969. A big factor was a book by Minsky and Papert.
What did they show?
They mathematically demonstrated that a basic single-layer perceptron couldn't solve certain problems, most famously the exclusive or XOR logical function. It seems simple, but the basic perceptron couldn't learn it.
And that dampened enthusiasm.
Significantly. Funding dried up in the U.S. for ANN research. But, and this is important, the source points out that this limitation only applied to those very basic perceptrons. Research on deeper, more complex networks was already happening elsewhere and wasn't affected by the XOR problem.
Ah, okay. So the progress didn't completely stop. It just shifted focus or location.
Precisely. And some really groundbreaking work on deep learning was actually happening during that supposed winter. For instance, the first working deep learning algorithm came out of the Soviet Union in 1965.
1965? Seriously? Deep learning?
Yep. Ivakhnenko and Lapa developed the group method of data handling. It trained deep networks, potentially arbitrarily deep, layer by layer, using techniques like polynomial regression. Their 1971 paper described an 8-layer deep network.
That's incredible. I had no idea it went back that far.
And around the same time, in Japan, Shunichi Amari was doing fundamental work. In 1967, he published research on training deep multilayer perceptrons using stochastic gradient descent.
Stochastic gradient descent, that's still used today, right?
Absolutely, it's a core optimization technique. And his
Ugh.
student ran experiments showing a 5-layer network could learn internal representations to solve problems like XOR that the basic perceptron couldn't. The field was moving forward.
And other key pieces were falling into place too, like activation functions.
Right. Kurihiko Fukushima, also in Japan, introduced the ReLU activation function in 1969, rectified linear unit. It's now probably the most popular activation function used in deep learning.
Wow.
And Fukushima didn't stop there. In 1979, he developed the neocognitron.
That sounds important.
It was a major precursor to modern convolutional neural networks, or CNNs. It had ideas like layers that performed convolutions, downsampling layers to reduce size, and shared weights. All key concepts in CNNs. It wasn't trained with backprop yet, but the architecture was there.
Okay, speaking of backpropagation, we mentioned it as the key training algorithm now. How did that come about? Was it invented for neural nets?
Actually, no. Backpropagation is basically just a very efficient way to apply the chain rule from calculus, which, believe it or not, goes back to Leibniz in the 1670s.
The 1600s. For backprop.
For the underlying math, yes.
Right.
Now, applying it in this context, Rosenblatt actually used the term backpropagating errors in 1962, but didn't really implement it in the modern sense. There were precursors in control theory, too, like from Kelly in 1960.
So who published the modern version?
The modern algorithm, the efficient reverse mode automatic differentiation, was published by Seppo Lennonmaa in Finland in his 1970 master's thesis, and later in 1976. It was a general technique.
Okay, so a general math tool. Who connected it to neural networks?
That was Paul Werbos. He applied it to ANNs in his 1974 PhD thesis. But it didn't really take off widely until 1986, when Rumelhart, Hinton, and Williams published their influential paper showing how effective backprop was for training multi-layer networks. That really popularized it.
Okay, so with backprop becoming known and architectures like Fukushima's neocognitron providing inspiration, people started building more powerful networks, like CNNs for images.
Exactly. Convolutional neural networks, CNNs, really took off, especially for computer vision tasks.
What makes them so good for images specifically?
It's those convolutional layers. They act like little feature detectors, scanning across the image, looking for specific patterns, edges, corners, textures, that kind of thing. And importantly, because of weight sharing, they detect the same pattern, regardless of where it appears in the image.
Ah, so position doesn't matter as much.
Right. And they also typically use pooling layers, like max pooling, which Fukushima's neocognitron also introduced to downsample the image, reducing the computational load while keeping the most important features.
And did people start getting good results with these early CNNs?
They did. Alex Wabel used a related idea called time delay neural networks, or TDNNs, for speech-specifically phone recognition back in 1987. It used convolutions and backprop.
Okay.
And Wei Zhang, between 88 and 94, published work applying backprop-trained CNNs to practical problems like recognizing letters of the alphabet, processing medical images, even breast cancer detection.
And then there was Lynette, right? That's a famous one.
Very famous. Jan LeCun and his colleagues developed Lynette around 1989, refined it in 98. It was used commercially by banks to read handwritten numbers on checks, ZIP codes, and digits.
Wow.
Yeah.
How long did it take to train back then?
The source mentions it took about 3 days to train Lynette 5 in 1998. Gives you a sense of how much faster compute has gotten.
Okay, so CNNs were great for images. What about data that comes in sequences, like text or maybe speech over time?
Yeah, for sequential data, a different type of architecture became important. Recurrent neural networks, or RNNs.
Recurrent, meaning they have loops.
Exactly. They have connections that loop back, either within a layer or to a previous layer. This allows the network to maintain an internal state or memory of past inputs, which is crucial for processing sequences where context and order matter.
Where did the ideas for RNNs come from?
Kind of a mix, really. Some inspiration came from statistical mechanics like Hopfield networks, which are a type of RNN, and also from neuroscience ideas about how the brain might use reverberating circuits for short-term memory. Go back to researchers like Codgel and Hebb. Even McCulloch and Pitts considered networks with cycles back in the 40s.
Interesting. The source mentions one called the crossbar adaptive array from 1982.
Ah, yes. That was a really interesting early RNN. It wasn't just about processing sequences. It introduced this concept of self-learning.
Self-learning? How?
It had a model where the network made decisions, cognition, but also had an internal evaluation of the consequences of those decisions, something akin to emotions or secondary reinforcement. It learned by adjusting its memory based on the interaction between its decisions and these internal evaluations, without needing explicit external rewards or labels for every step.
That sounds quite advanced for 1982, a model of cognition and emotion interacting.
It was quite forward-thinking, yeah. It even contributed to debates in cognitive psychology at the time.
Right.
Later RNNs, like the Jordan network and Elman network, were also applied to cognitive modeling.
But RNNs had their own challenges, right? Especially training deep ones.
Oh, yes. The big one that emerged in the 80s when people tried using backprop with RNNs for longer sequences was the vanishing gradient problem.
Right, I've heard of that. The error signal gets weaker and weaker as it flows back through time.
Exactly. The gradients for connections far back in the sequence become tiny, almost zero. So the network basically couldn't learn long-range dependencies. It was a major bottleneck.
So how did they overcome that?
There were several key breakthroughs. Jürgen Schmidhuber did some important early work in the early 90s, developing methods like a neural history compressor that used unsupervised pre-training and could handle very deep sequences equivalent to over 1,000 layers unfolded in time by 1993.
Wow.
And Sip Holkreiter, in his 1991 diploma thesis, formally identified and analyzed the vanishing gradient problem. He also proposed solutions like recurrent residual connections,
Which led
directly to one of the most influential RNN architectures ever, long short-term memory, or LSTM. Hochreiter and Schmidhuber developed LSTMs together, publishing in 1995.
And LSTM specifically tackled the vanishing gradient.
Yes, they were designed with internal gates like forget gates, input gates, output gates that control the flow of information and gradients, allowing them to selectively remember or forget information over long periods. They became incredibly successful and set accuracy records on many sequence tasks.
The modern version with the forget gate came a bit later.
Yeah, the standard LSTM architecture most people use today, with the explicit forget gate, solidified around 1999. For a long time, LSTMs were pretty much the default choice for deep learning on sequences.
Okay, so we had CNNs, we had LSTMs solving the RNN problem.
Yep.
All these pieces were developing over decades. What caused the huge explosion in deep learning that we've seen more recently, say, in the last 10, 15 years?
It was really a perfect storm of factors coming together, kind of kicking off around 2009 to 2012.
What were the main ingredients?
Well, one massive factor was compute power, specifically GPUs.
Graphics processing units.
Right.
Used for video games originally.
Exactly. But researchers realized that the highly parallel architecture of GPUs designed for rendering graphics was also incredibly well-suited for the matrix multiplications and other calculations needed to train large neural networks.
So they repurposed gaming hardware.
Pretty much. GPUs offered orders of magnitude millions of times, potentially more parallel processing power for these specific tasks compared to traditional CPUs at the time. Suddenly, training much larger and deeper networks became feasible.
And you need big networks for big data.
That was the second ingredient. The explosion of big data, the internet, digital sensors. Suddenly, we had massive data sets available to train these networks on. More data generally means better performance, especially for deep models that have millions of parameters to learn.
So powerful hardware met massive data sets. Anything else?
Algorithmic refinements helped too. People figured out better ways to initialize weights, use activation functions like RILU, and apply techniques like dropout for regularization. And combining these, like using backprop on deep CNNs accelerated by GPUs, that was a winning formula.
Like Sir San and colleagues in 2011 getting superhuman performance.
Yes, their work showed that deep CNNs on GPUs could really push the boundaries, winning visual pattern recognition contests, even beating human performance on some benchmarks for the first time.
And then the really big watershed moment for many was AlexNet in 2012.
Absolutely. Krzyzewski, Sutskever, and Hinton's AlexNet won the ImageNet competition, a huge image recognition challenge by such a significant margin compared to previous methods. It really woke everyone up to the power of deep learning. It wasn't just incremental progress, it was a leap.
And that spurred a lot more research and development.
Totally. After AlexNet, you saw a rapid development of even deeper and more sophisticated CNNs like VGGNet and Google's Inception networks.
And it wasn't just about labeled data, right? Andrew Nang and Jeff Dean's famous cat experiment.
Right. That was also around 2012. They showed that a large network, trained on unlabeled images from YouTube videos, could spontaneously learn to detect high-level concepts, like human faces and, famously, cats, without ever being told what a cat was.
Demonstrating the power of unsupervised learning at scale.
Exactly. This period also saw generative models take a huge leap forward with generative adversarial networks, GANs, introduced by Ian Goodfellow and his team in 2014.
The ones where two networks play a game, one generating fakes, one trying to spot them.
That's the essence of it, yeah.
Mm-hmm.
A generator tries to create realistic data, like images, and a discriminator tries to tell the difference between the generator's fakes and real data. As they train against each other, the generator gets better at making realistic fakes, and the discriminator gets better at spotting them.
Though the source mentions Schmidhuber had a similar competing network idea way back in '91.
Yes, an earlier concept of artificial curiosity involving two networks in a zero-sum game. But GANs really captured the imagination and led to stunning results in image generation, things like Stylogan. Of course, they also fueled concerns about deepfakes.
And now diffusion models seem to be leading in image generation, like Della 2, Stable Diffusion.
Yeah, diffusion models, which came along starting around 2015 and really took off recently, have generally surpassed GANs in terms of image quality and training stability for many tasks. They work differently by gradually adding noise to images and then learning to reverse the process.
As networks got deeper, like 20, 30 layers around 2014, new problems arose, like degradation.
Right. Counterintuitively, just stacking more and more layers sometimes made performance worse. Even on the training data, the optimization became harder.
How did they fix that?
With some clever architectural innovations. One was the highway network, and even more influential was the residual neural network, or ResNet, developed by Kaming He and colleagues in 2015.
ResNet, what did that do?
It introduced skip connections, or residual connections. These connections allow the input to a block of layers to be added directly to the output of that block, essentially letting the network easily learn an identity mapping just passing the input through unchanged. This made it much easier to train very deep networks, hundreds or even over 1,000 layers deep, without degradation. ResNets were revolutionary.
And that brings us almost to the present, with the rise of the transformer architecture, especially for language.
Absolutely. Transformers, introduced in the seminal 2017 paper Attention is All You Need, basically took over natural language processing, and now many other fields too.
What was the key idea there?
They combined ideas from sequence-to-sequence models with a powerful mechanism called self-attention. Attention allows the network to weigh the importance of different parts of the input sequence when processing any given part. Unlike RNNs, which process sequences step by step, transformers can process all parts of the sequence in parallel, making them much faster to train on modern hardware.
Though the standard transformer scales quadratically with sequence length, the source mentioned an earlier linear scaling equivalent.
Yeah, it notes Schmidhuber's 1992 work on fast-weight controllers scaled linearly and was later shown to be mathematically equivalent to what's now called a linear transformer. But the standard attention mechanism in the 2017 paper, despite quadratic scaling, was incredibly effective and easier to parallelize.
And this transformer architecture is what's behind models like ChatGPT, GPT-4, BERT.
Exactly. It's the foundation for most of the large language models and many other state-of-the-art AI systems today. It really represents the culmination, so far, of this long and fascinating history of development.
It really is an amazing journey, isn't it? From, least squares 200 years ago, through the biological inspiration, the ups and downs, to these incredibly complex transformers. Let's maybe circle back and solidify some of the mechanics we touched on earlier.
Sure. It always comes back to that basic building block.
Mm.
The artificial neuron, you've got inputs, connection weights, maybe a bias term. They get summed up, pass through that nonlinear activation function, and produce an output.
Right, and they're arranged in layers. Input, hidden, output. And the connections can be different, right? Not always everything connected to
No,
everything.
not. You have fully connected layers, yes, where every neuron in one layer connects to every neuron in the next. But CNNs use those specialized convolutional connections that share weights and pooling layers that summarize regions. The connection pattern is part of the architecture design.
And we have feed-forward networks, where information flows straight through.
Like a directed acyclic graph, yeah. Simple flow.
Versus recurrent networks, the RNNs, with those loops allowing for memory and sequence processing.
Exactly. The structure really defines the network's capabilities.
Okay, and you made the distinction between parameters and hyperparameters. Parameters are what the network learns.
Right. Weights and biases. Those are adjusted during training based on the data.
And hyperparameters are set before training?
Yes. They're the knobs you turn to configure the learning process itself. Things like the learning rate, how big the adjustment steps are, or the number of hidden layers, the number of neurons in each layer, the batch size, how many examples you process before updating weights. Choosing good hyperparameters is crucial and often requires experimentation.
Got it. And the learning itself always involves minimizing that cost function, measuring the error.
Pretty much always in supervised and unsupervised learning, yeah. The cost function tells you how well the network is doing. You calculate the gradient of this cost function with respect to the parameters using backpropagation.
And then you use an optimization algorithm like stochastic gradient descent or variations like Atom to update the parameters in the direction that reduces the cost.
Exactly. And that learning rate hyperparameter controls the size of those update steps. Too high, you might overshoot or bounce around. Too low, training takes forever or gets stuck.
So finding the right learning rate is key. You mentioned adaptive rates and momentum.
Yeah, modern optimizers often adapts the learning rate dynamically during training, and momentum helps the updates continue in a consistent direction, smoothing out the process and potentially helping escape shallow local minima.
Okay, so beyond the mechanics of backprop, the source mentioned different broad approaches or paradigms for learning.
Right, the three main ones usually discussed are supervised, unsupervised, and reinforcement learning.
Supervised is the one with labeled data, like flashcards.
Exactly. You provide the network with input examples and the corresponding correct output labels. Input image of a cat, label cat. Input house features, label price. The network learns to map inputs to the correct outputs.
Used for classification and regression?
Primarily, yes. Pattern recognition, predicting values, understanding sequences like text or speech when you have transcripts.
Then unsupervised learning. No labels this time.
Correct. You just give the network the input data and let it try to find structure or patterns within that data on its own. There's no right answer provided externally.
So what's the goal then?
Often, things like clustering, grouping similar data points together, or dimensionality reduction, finding a more compact representation of the data, like compression, or density estimation, learning the underlying probability distribution of the data. It's about discovering inherent structure.
Okay. And the third one, reinforcement learning. Learning by doing.
That's a good way to think of it. It's about an agent, the network, learning to make decisions by interacting with an environment.
Like the robot learning to walk example.
Perfect example. The agent takes an action, moves a leg, the environment changes state, and the agent receives a reward or penalty. Did it stay balanced? Did it fall? The goal is to learn a policy, a strategy for choosing actions that maximizes the total accumulated reward over time.
So it learns through trial and error, essentially, figuring out what actions lead to good outcomes.
Pretty much. There's often a balance between exploring new actions to see what happens and exploiting actions it already knows are good. It's used heavily in robotics, game playing, resource management, complex control problems.
And you mentioned that self-learning idea from the crossbar adaptive array again. How does that fit in?
It's related to RL but distinct because in that specific 1982 model, the reinforcement wasn't external. It learned based on the internal evaluation, the emotion associated with the consequence of its action, not a direct reward signal from outside. It was learning from the interaction of its own cognitive and emotional states.
Fascinating. A different flavor of learning.
Yeah. And there are other approaches too. Neuroevolution uses evolutionary algorithms, like genetic algorithms, to evolve the network structure and weights, which can sometimes outperform gradient descent.
And stochastic neural networks. Introducing randomness.
Right. They intentionally add noise during processing or learning, which can help them escape local minima and potentially find better solutions. And topological deep learning tries to incorporate mathematical topology to better handle complex data relationships.
And even how you update matters. Stochastic versus batch.
Yes. Stochastic updates weights after every single example, noisy but can explore well. Batch updates after seeing the entire data set stable but slow and might get stuck. Mini-batch learning, updating after small batches, is the common compromise, balancing speed, stability, and exploration.
Okay, so with all these choices, architecture, learning paradigm, hyperparameters, designing a network sounds like a real challenge. It's not just grabbing something off the shelf.
Oh, definitely not. It's still very much a process that requires expertise. You need to understand the problem, the characteristics of your data, the trade-offs between different models. Do you need a CNN, an RNN, a transformer, something else? How many layers? How many neurons? How should they be connected?
Lots of decisions.
Tons. And complex models might perform better, but take much longer to train and require more data. Then you have to choose the right cost function, the right optimizer, tune all those hyperparameters.
And it's mostly trial and error.
There's a significant amount of experimentation involved, yeah. Trying different configurations, seeing how they perform, especially on data they haven't seen before. That generalization piece is key. Building a robust, reliable network takes careful design and validation.
Is this getting any easier? Is automation helping?
It is, somewhat. There's a whole field called neural architecture search, or NAS, where machine learning techniques are used to automatically search for good network architectures for a given task.
So AI designing AI.
Kind of, yeah. Tools like AutoML and AutoKeras try to automate parts of this process. They can often find architectures that perform as well as, or sometimes even better than, human-designed ones. But even NAS usually operates within constraints and search spaces defined by humans. It's not fully automated magic yet.
And that Python snippet we mentioned earlier fits into this picture how?
It's just illustrating the core computation that happens inside the training loop. Once you've designed the network and chosen the hyperparameters, it shows the flow. Take input, calculate output, calculate error, calculate gradients via backprop, update weights. That's the engine running during training.
Okay, so all this complex machinery, this long history, it leads us to today, where these ANNs seem to be everywhere. What makes them so broadly applicable?
It really comes down to that core strength. Their ability to learn complex nonlinear patterns directly from data. They can model relationships that are incredibly difficult, maybe impossible to capture with traditional rule-based programming.
They find the patterns themselves.
Exactly. And that makes them useful in an enormous range of fields, as the source material highlights.
Yeah, let's run through some of those applications mentioned.
Okay, well, core tasks like function approximation and regression, basically learning mappings between inputs and outputs, like predicting future values in a time series. Data processing, things like noise filtering, data clustering, data compression, finding structure, and simplifying data.
Control systems, like self-driving cars.
That's a big area, yeah. Vehicle control, adaptive robotics, process control in industry. Pattern recognition is maybe one of the most visible areas. Facial recognition, object detection in photos and videos, analyzing medical images like X-rays or MRIs.
Huge impact there.
Sequence recognition, too, which we discussed with RNNs and transformers, speech-to-text, machine translation, handwriting analysis.
Robotics, controlling robot arms, prosthetics.
Yep. Data mining, finding hidden insights in massive business or scientific data sets.
The source specifically called out finance.
Yes, finance uses ANNs extensively for processing huge amounts of financial data to spot subtle patterns, predict stock market movements, assess credit risk, detect fraud, personalize financial advice. They can automate lending decisions based on complex profiles.
But there are challenges there, right?
Yeah.
The black box problem.
Definitely. Data quality is critical in finance. Tuning the models takes expertise. And yes, the interpretability issue, why did the model deny this loan, can be a major hurdle for regulation and trust.
And medicine is another huge area.
Absolutely. Analyzing medical images for detecting tumors or other anomalies. Predicting patient outcomes based on their history and test results. Helping design personalized treatment plans. Even accelerating drug discovery by predicting how well potential drug molecules might work or what side effects they might have. Personalized medicine is a big driver.
Similar challenges, though. Privacy, interpretability.
Huge challenges. Patient data privacy is paramount. And a doctor needs to understand why an AI is recommending a certain diagnosis or treatment before they can trust and act on it. Explainability is crucial in medicine.
What about content creation? That feels very current.
Yeah, models like JANs and transformers are being used to generate art, music, text, even code. You see AI composing music, generating realistic images from text descriptions like DALL-E, writing articles. They're used in advertising, predicting film success, even making video game characters behave more realistically.
Cybersecurity, too. Fighting the bad guys.
Increasingly, yes. Using ANNs to distinguish normal network traffic from malicious activity, classify new types of malware, identify phishing websites or domains used by attackers, detect fraud, and botnets. It's an ongoing arms race, using AI on both sides.
And even basic science, physics, brain research.
Yeah, researchers are using them as tools to solve complex equations in physics, simulate quantum systems. And in neuroscience, ANNs serve as computational models to test hypotheses about how biological brains might work, how neurons compute, how circuits give rise to behavior, how learning and memory happen.
And material science finding new materials.
Right. The source mentioned using graph neural networks, which are good for structured data like molecules, to predict the properties of materials and potentially accelerate the discovery of new ones with desired characteristics, like stability or energy storage capacity.
So the applications are incredibly broad and powerful. But we should also touch on the theoretical side and the criticisms. What do we actually know about their fundamental limits or properties?
That's a good question. Theoretically, we know some things. The universal approximation theorem is a big one.
Remind me.
It basically says that a standard feed-forward network with just one hidden layer, given enough neurons, can approximate any continuous function to arbitrary accuracy.
So in theory, they can learn anything.
Any continuous function, yes. But the theorem doesn't tell you how many neurons you need or what the weights should be or how to find them. It's more of an existence proof. It shows the potential is there.
Okay. And capacity.
Capacity relates to how much information a network can store or how complex a function it can represent. It's related to the number of parameters, the architecture. There are theoretical measures like VC dimension to try and quantify this.
Do they always find the absolute best solution when training? Convergence.
That's a major theoretical and practical challenge. They use optimization techniques like gradient descent, but those methods aren't guaranteed to find the global minimum of the cost function. They can get stuck in local minima or slow down on saddle points, especially in the very high-dimensional complex landscapes of deep networks. Convergence to the best solution isn't guaranteed.
And generalization performing well on new data is tied into this, right? Overfitting.
Absolutely. That's maybe the biggest practical challenge. You need the network to learn the underlying pattern, not just memorize the training data. If the network is too complex relative to the amount of data, high capacity, it can overfit badly.
Like the student memorizing answers again.
Exactly. So techniques like cross-validation are vital, using a separate validation data set to check performance on unseen examples during training and help tune hyperparameters like the model complexity or regularization strength. Regularization itself adds penalties to the cost function to discourage overly complex models.
Okay, let's turn to the criticisms. It's important to look at the downsides or limitations.
Definitely. No technology is perfect.
One big practical one seems to be the need for lots of data.
Yes, especially for complex tasks in the real world, deep learning models often require huge amounts of labeled training data to perform reliably. Gathering and labeling that data can be expensive and time-consuming.
Though the source mentioned ways to mitigate that. Data augmentation, transfer learning.
Right. Techniques like augmenting existing data, rotating images, adding noise, using mini-batches, transfer learning, reusing parts of models trained on other tasks, active learning, intelligently selecting which data to label, can help reduce the data hunger somewhat.
What about the criticism that the theory is lacking, that it's more engineering than science, or even magic?
Yeah, that criticism's been around for a while. The idea that because we don't always have a deep first principles understanding of why a particular set of learned weights works so well, it feels less like traditional science and more like sophisticated tinkering or finding solutions that emerge as if by magic.
The something-for-nothing critique?
Kind of. The counterargument is, well, look at the results. They solve incredibly complex problems that were intractable before. And while they're not biological brains, they're complex systems we can analyze. Plus, the field of explainable AI, XAI, is actively working on developing techniques to peer inside the black box, like using attention maps to see what parts of the input the network focused on. We are gaining some insights into their internal workings.
Hardware was another historical criticism, needing massive compute power.
It was a huge bottleneck for decades. The current deep learning boom is inseparable from the hardware revolution GPUs first, and now specialized accelerators like TPUs, tensor processing units, and other AI chips. These have made training large models feasible. Neuromorphic engineering is trying to push this further by building chips that mimic brain structures directly for efficiency.
Some argue for hybrid approaches, combining neural nets with older symbolic AI.
Yes, there's a school of thought that believes the strengths are complementary. Neural nets are great at perception, pattern matching, learning from raw data. Symbolic AI is traditionally better at logical reasoning, planning, using explicit knowledge. Some researchers believe combining them might lead to more robust and human-like intelligence.
And maybe the most critical issue today? Dataset bias.
This is a massive concern, and rightly so. ANNs learn from the data they're given. If that data reflects societal biases, historical discrimination in hiring, racial bias in facial recognition data, gender stereotypes in text, the network will learn those biases and perpetuate them, potentially amplifying them.
Like the Amazon recruiting tool example.
Exactly. Trained on past hiring data, it reportedly learned to penalize resumes that included keywords associated with women, because historically fewer women were hired in those tech roles. This can lead to real-world discriminatory outcomes in sensitive areas like hiring, loan applications, even criminal justice risk assessment. It's a critical ethical challenge.
Can anything be done? The source mentioned synthetic data.
Mitigating bias is an active area of research. Carefully curating data sets, auditing models for bias, developing fairness-aware algorithms are all part of the effort. Using synthetic data, artificially generated data, can sometimes help create more balanced data sets or fill gaps where certain groups are underrepresented in real-world data, which might help reduce bias.
Right.
But it's a complex problem with no easy fix.
Wow. Okay, we have really covered a huge amount of ground today.
We certainly have. From the very beginnings, that biological spark, the long history with its ups and downs.
Through the different architectures like CNNs, RNNs, LSTMs, transformers, how they learn with backpropagation.
The different learning paradigms, supervised, unsupervised, reinforcement learning, even self-learning.
To the incredible range of applications we see now, changing almost every field.
But also, importantly, looking at the challenges.
Yeah.
The data needs, the computational cost, the black box problem of interpretability.
And that critical issue of bias baked into the data, leading to potentially unfair outcomes.
So yeah, thinking about all of that, the immense power and potential, but also the inherent risks and limitations,
Yeah.
it really makes you think about the future.
Absolutely. So here's a final thought for you, our listeners, to chew on based on everything we've discussed today. Given the incredible capabilities and pervasive spread of these artificial neural networks, but acknowledging their deep dependence on data that might be biased, and the real challenges we still face in fully understanding why they make the decisions they do, how should we as a society think about building, deploying, regulating, and ultimately trusting these increasingly powerful artificial systems as we move forward?